Stat 3617. Okay, this week I'm going to talk about the first sampling scheme, the simple random sampling. Before we go into the sampling scheme, I'd like to emphasize that all of the sampling scheme that we will talk about, they are all under the scope of the probability sampling. What is probability sampling? We'll have a look at that. First of all, we need to have a target population that we want to describe about. So like, for example, we want to describe about the spending pattern of a particular estate. Let's say we want to know about the weekly spending pattern or how much they spend for those residents who live in Taikoo Shing. So we have a target population. We want to describe about that. And then we decide the variable of interest, like the weekly spending. And then we have the population of n members. Suppose that we obtain a list of the residents who live in Taikoo Shing. So y1, y2, y3, up to yn will be labeled for each of the residents who live in Taikoo Shing. And y1 would be the first resident who, with the weekly spending that we interview them, and then we obtain the value. Y can be any kinds of variable of interest. For example, monthly spending, weekly spending, or even the number of hours they spend watching the TV, etc. Okay. So for the population characteristics, we can use some of the parameter to describe about. Again, like the Y variables is the weekly spending. Then we can add up, like for each of the residents, we interview them. Then we add up the total of the spending. Then we can estimate the total weekly spending of the entire estate or the entire population. Mean, or trying to make it more meaningful, sometimes we like to look at the average. So we have the total divided by the total number of residents. And so we have Y bar. Proportion, sometimes we like to ask about what is the proportion of the household who owns a car, or what's the proportion of the household that own their own house, right? So we can again look at the proportion, then we can calculate the total proportion of the entire population. So you can notice that we are trying to use the capital letter as the notation for the true population variables. So like the capital T, capital Y bar, capital P, to indicate those are the true population values. Since we are not going to ask everybody in the entire population, that's why we do a sample survey. So we want to estimate those characters from a sample. So assuming we collect a sample, let's say SA, of the size n from the population. Size n, we can determine what is the size of sample we want to collect from the population. If size n is relatively smaller than the population size, then you can imagine that would be a number of samples, different samples that we can collect. And probability of each of the sample that we collect to be our sample survey would have the same probability. And the number of possible sample depends on how we draw the samples. So the number of sample depends on whether we draw each of the residents without replacement or with replacement. Let's first look at the with replacement case. With replacement, that means a particular sample unit has been drawn randomly from the population, and then that sample unit was put back to the sampling list. Then he could have a chance of being selected again. So this is with replacement. And you can imagine that we would have in that case, usually the statisticians would refer it as the infinite population. Without replacement, it's more likely to be in our reality case for the sample survey, like the sample unit has been drawn from the population, and then its name is not going to put back to the frame, and then we draw the second candidate, the second sample unit. So if that's the case, you can imagine if you were selected to be interviewed, then you won't be selected to be interviewed again. So trying to avoid the same person being interviewed. Both could be applicable in sample survey, but usually more practically, we will use the without replacement, or we assume we have a finite population case. And that later on we will show this is more efficient than the infinite case. Okay, so this table in the text actually shows the number of possible samples that we can form, but again, we can have the probability of each of the sample to be selected. Infinite population case with replacement. So we want to estimate the population characteristics, assuming that we select the sample. Let's say SA was selected with the size of n. So within the sample, we could have each sample unit. So a particular person, Y1, Y2, Y1 could appear here because we have with replacement selection, right? But again, from each of the data, we can look at the data itself. This is our sample. We can add up to have a sample total. We can take the average. We have a sample average, a proportion of our sample, etc. So bear in mind, every sample unit, Y1, Y2, or even Y1 again, every time they were chosen, have an equal chance of being chosen. Okay, and since we are doing with replacement, so every sample unit drawn is independent with each other. In that case, we can look at the covariance between the sample units with equals to 0. However, in our sample survey, we would assume we have a finite population. So we drew the sample without replacement. Again, we want to select a sample, let's say SB, another sample, drawn randomly. And then within the sample SB, let's say we have a size of Y1, Y2 up to Yn, again size n, without replacement. So Y1 appear once here, and he's not going to be selected again to be appear in the entire sample. Without replacement or finite population, again, each of the sample units would have the same chance of being chosen. And each sample unit would depend on each other. You can think about that why it is the case. Okay, so if this is the case, they are being depend from the previous or the already chosen sample unit. The covariance of yi to yj, they does not equal to 0 anymore because that depends on each other being chosen. So if this is the case, we can form a different estimated variance of the sample mean, and then we could have a relatively more efficient calculation of the of my sampling scheme. But we can come back to that. Why? Under the finite population, it is relatively more efficient than the infinite population. Okay, so throughout the course, throughout this step 3617, or all the sampling scheme we talk about, we would assume that we are dealing with a finite population case, that we know the capital N, the number of sample unit in the size of our population. Okay, so we are doing that without replacement, and we are referring that as the finite population. Then among the different sampling scheme, how are we going to choose the best one? Like the simple random sampling, stratified random sampling, etc., etc. Which one is the best? The broad aim of sampling theory is to devise the sampling schemes which are economical, so this is not going to be very expensive, easy to operate, and yield unbiased estimators. This is very important. That's we have the target population, we target the right sample, then we are trying to minimize the bias with the estimator. And lastly, most importantly, is to minimize the effects of the sampling variations. So we look for the least variance or the estimated variance we can be obtained from that particular sampling scheme, and then we chose that one. Okay, particular sample can be chosen with that probability sampling scheme. So with that, we would say under a particular sampling scheme, the sample estimator theta hat is the unbiased estimate of the population parameter theta. So in this case, if I estimate the average under the simple random sampling, let's say, then we would say the expected value of our sample mean obtained from simple random sampling would be equals to the population mean mu. In this case, they are the unbiased estimator to the population parameter. If, under that particular sampling scheme, the sample size is relatively large enough, so n is large enough, the estimator theta hat would be normally distributed. Okay, so apart from the text, I tried to add some additional graph for you to understand what happened in the populations and the sample. So what we're trying to say is, in this graph, you can see, assuming this is the population, okay? The population goes from 1 to all the way to 10. So the mean is 5.5, okay? So we don't have a normally distributed, or this is a unified distribution of the population, okay? So if we want to describe about the population, we know that the mean is 5.5. So let's say mu is 5.5. Okay, so we randomly choose some of the sample from the population. Let's say we choose a particular sample of size n equals to 10. So we choose 1 guy, 2 guys, 3 guys, up to 10 guys, okay? And then take the average y bar and then put it down in here. And then if we keep repeating that, like we repeatedly doing a sample survey from the population, like 500 times, then for each of the 500 samples, we take the means, and then we would obtain a y bar distribution. Okay, so this is the y bar or the sample means distribution. We can see that the y bar distribution seems to center in the middle, somewhere near 5.5, 5.6. Okay. So what I'm trying to say is, like, if we do the same, but with the sample size, every time we draw 25 samples, and then we obtain the y bar, and then if we repeat it 500 times, we have 500 y bars, and then we have another distributions. Sample size of 50. So we're trying to show that if we increase the sample size, we would end up having a more centrally, having a higher central tendency, with the expected y bar would be the unbiased estimator equals to mu. So we can see that expected y bar is around 5.6, 5.5. That would be closest to the mu, which is a 5.5 value, the true value in the population. Then we can also show that if we keep increasing the sample size, that we are having a more tipped in the middle, so they are more centrally concentrated to the mean value. What does it say? It also shows that the dispersion or the variations of the distributions has been changed from n equals to 10, and then we get a more narrower distribution when n equals to 30, and even more precise estimate towards mu when we have the sample size of 50. So the variance of my sample mean would be smaller. Okay, so this is why it explains why usually it's preferable that we collect more data from our sample, as the